Howdy, y'all. My name is Junior Pham. I'm a material science engineering at A&M, and today I'll be talking about using cascade molecular dynamic simulation to study the mechanical field effects of simple defects on irradiated materials. I want to thank my sponsors, Los Alamos National Laboratory and the OREU program at A&M, and I want to thank my mentors, Kandang and Darshan Bamni. So here's just an outline of how my presentation will go and like the order that it'll be in. And let's just start off with the motivation. So why am I doing this? Well, we've all heard of AI, right? It's something we may use because it's efficient, it has a lot of available information, and it has a lot of potential economic and societal benefits. Although AI is very useful, it's starting to use up a lot more energy due to having to store and process so much data. So a potential solution that we can use are mini reactors, mini nuclear reactors. They can't be really big because we aren't trying to power cities. Instead, we need an advanced, compact nuclear reactor that can is both sustainable and energy efficient in computing. So the first step to making this sustainable is a material that can handle radiation damage. So how can we find this? Well, we can model it. So to find the material, we can either do normal experimentation or modeling at atomistic simulation. The only issue with normal experimentation is that it takes a lot of time, a lot of money, and can be potentially risky, especially in extreme conditions like radiation. Atomistic simulation can model normal experimentation quickly, affordably, and without that risk. So some advantages of atomistic simulation include its atomic resolution, which just allows it to capture atomic level interactions, which just tells you like its ability to capture the radiation cascade at the atomic level as well. Atomistic simulation can model high energy particles that collide with the lattice of the structure, which causes a collision cascade. And the simulation, though initially simple, can be improved to the CRA method, the creation relaxation algorithm, which can increase processing efficiency and therefore allow for larger model volumes and larger radiation doses. So let's talk about what I'm going to be modeling this on. Well, I'm going to be using LAMPS, which stands for Large Scale Atomic Molecular Massively Parallel Simulator, through TAMU's HPRC High Performance Research Computing Grace Cluster. LAMPS can model real-time material behavior through solving Newton's equations, such as F equals ma, shown on the top equation, and F equals the negative derivative of the potential energy, the second equation. Some assumptions that LAMPS makes are that atoms are point masses and that classical forces are used, so quantum forces are not accounted for. LAMPS can predict many material properties, such as diffusion coefficients and melting temperature. Things that it can predict are thermodynamical properties, structural properties, mechanical properties, diffusion properties, and phase transition properties. LAMPS can also work by parallel computing, which just means splitting the initial simulation box into multiple subdomains, which allows each processor to calculate atomic interactions within those small subdomains, which enables LAMPS to process large and complex simulations more efficiently with more processors. Okay, and then how did I use LAMPS first, or how did I test it? I first used tensile and compression examples with aluminum at 300 Kelvin. The first two images on the left side show the atomic structure before and after tension, which doesn't seem like much has happened. But if you look at the compression example and removing the FCC lattice points, we can see the development of defects. This, you can see the development of the planes, as well as how compression affects the material. And in the future, we can see how radiation affects the material. So let's talk about cascade molecular dynamics. So what exactly is this? Well, cascade molecular dynamics models radiation damage through the use of a primary knock-on atom, which is the first atom that is displaced by an energetic particle such as neutrons and ions. The way radiation damage works is a high energy particle will collide with the lattice, which causes a chain reaction of atomic displacement, also known as cascade, which is what cascade molecular dynamics models. So the way I approached modeling cascade molecular dynamics was to first try to recreate the cascade where the pK hits the material, but consistently the pK would stick to the material. I also tried starting the pK in the middle, but I did not see any cascade. So I used a working script that depicted cascade and adapted it to fit my needs. For example, the script used tungsten as element, so I changed our parameters to fit a cascade for iron. This would include changing things such as lattice parameter and the potential. I also adapted the script to evolve, run 3 different energies, and run 3 different temperatures. Although the initial trials worked, the final cascade did not go as planned, so there are not valuable results that I can show you. Most likely due to the lack of energy. As seen on the left, they used 5 mega electron volts in their script, but I only used 5 kilo electron volts to 15 kilo electron volts. So that's most likely why it didn't work. In the future, I hope to use much higher energies, and hopefully it'll work then. Okay, so what are the cons of cascade? Although cascade characterizes realistic damage, it takes a lot of time and money to run multiple cascades. Plus, multiple cascades are necessary. To get meaningful results, you need an average of about 10 to 20 different cascades, all with different pKa's that have different energies and directions. This also only characterizes the first picoseconds of radiation, when radiation can happen over many, many years. The many cascades as well as expensive computationally and monetarily. For cascades to be meaningful, the simulation boxes have to be large, which means simulating hundreds of thousands to millions of atoms, which just means way more force calculations. Cascade also require system evolution, which takes even more time and computation. In terms of monetary cost, these cascades can consume a lot of CPU core hours, which can take thousands of service units through HPRC and actual money if you're renting computation time. So how can CRA help us with these things? So let's talk about it. An advantage of CRA is that it can condense hundreds of cascades into one simulation, which saves time and money. Initializing the system is also very easy and versatile. You can change many parameters such as defects, and also defect location. Since you don't have to compute high-energy collision cascade, the computation is not as time-intensive. Another thing about cascade and CRA is that they can be used together, just like peanut butter and jelly. For example, after running 10 to 15 cascades, you can average the runs to obtain data on defect formation, which then can be scaled to much larger simulation boxes after you use CRA to scale it up. You can also use CRA to create damage on a material and run cascade on the damaged material. So in summary, CRA is good at scaling up cascade molecular dynamics to much larger systems, as well as being used to test cascade on stable configurations of irradiated materials. So, to model CRA, I first tried to move an atom from one site to its interstitial site, but realized that allowing the atom to relax after moving it to a random place within the material will allow for atoms to move to their natural positions. After this, I scripted the process to add Frankel pairs until my desired canonical displacement per atom is reached, for which the calculation for is Frankel pairs divided by total atoms. Canonical displacement per atom, or CDPA, is just a measurement of radiation, a unitless one. For my first simulations, I tested the system with aluminum parameters and transitioned to iron parameters. It's important for me to test iron as the material, which was also talked about in the cascade portion of my presentation, because steel is an important structural component of nuclear reactors, and guess what steel is made out of? Iron. So the first problems I encountered were inaccurate amounts of Frankel pairs to CTPA, which was caused by a randomization error in the code, which I fixed. And the simulation also did not track natural system evolution, so I included system evolution at the end of the code after creating the desired amount of Frankel pairs. In my case, the CRA runs were successful, so here are some examples of selected radiation dosages. So as you can see, there's a GIF that shows Frankel pair insertions as well as how the system evolves over time under constant temperature conditions. So the top left shows 0.00001 CTPA, the top right shows 0.00005 CTPA, and the bottom shows 0.0001 CTPA. If that was confusing, the CTPAs are also on the top. Some cool things you can notice is the difference in movement of atoms between the different temperatures. As you can see with 300, it doesn't move quite as much as it does for the 1000 Kelvin. I'll show you the next slide so it's a little bit easier to see. If you look closely, the evolution of the system does cause changes in the position of the Frankel pairs. Before the evolution, the system may not accurately show the evolution of defects. With the evolution, however, at the end, we can see how the defects move and therefore the most stable configuration for the defects. So as you can see here, the development of the Frankel pairs on the left side, the vacancy and interstitial. And on the right side, you can see the clusters developing as well. I'm gonna let this run for a little bit longer so you can see like how the temperature affects everything, and also how the defects move. As you can see, it's moving a little bit. Sometimes, you'll notice that the clusters split up a little bit. As well on the left side, you can see that the pairs kind of split up a little bit as well. It might be hard to see, but that's what's happening. And you can see on the right side as well. The defects are forming, and also the atoms are moving a lot more because of the high temperature. So let's talk about the key takeaways in future work. So some key takeaways are that AI is growing and we need more power to store it and process data, at least. So we can do this through nuclear power, but we need to develop material that can withstand radiation, these extreme conditions. So to do this, we can model it through an atomistic simulation, which would be safer, more time efficient, and more affordable. Modeling can simulate a simple radiation cascade and improve through the use of the CRA method, which allows for more efficient cascade and a relaxation simulation. As of right now, I'm still just getting started with lamps, as I said before, and in the future, I have to simulate much larger volumes of irradiated material and study the mechanical effects that simple defects can have on materials in terms of radiation damage. Thank you so much for listening to my presentation. Here are my citations, which includes any information about radiation cascade and also the images that I use. Have a great day.